Thanks very much. Thanks for letting me do it remotely. So I'm going to try and give a more general talk about different CDR technologies, carbon dioxide removal technologies, and saying a little bit about how I see the trade-offs. And I'll even start one layer up from that. People often talk about geoengineering, and traditionally a lot of these technologies have been talked about as geoengineering. In the IPCC context, for example, they're still considered very tightly linked. I think there's essentially no useful sense in which carbon dioxide removal technologies and these technologies for solar radiation management, I don't think that they are any more similar than either of them is to mitigation or adaptation. They are just different ways to go at the problem. That's not a statement about better or worse, but they are utterly different with respect to the kinds of technology involved, the distribution of winners and losers and risks in space and time. They are so distinct that I think it is very ineffective to treat them as the same thing, which in this conference you're not, but they often are, so I thought it was worth saying that. So now I'll talk a little bit about how I see some of the trade-offs between different CDR technologies. So as it happens, maybe it's worth saying, I've personally worked on biomass with CCS. I had one of my PhD students who's one of the first PhDs in that area, and I spent a fair amount of time working on it. And indeed, I do a little bit of work on it commercially still with that student, Jamie Rhodes. And I also work on direct air capture and on some of the other bits, but not very seriously. So I think that the fundamental uncertainties and sort of challenges around biomass with CCS are obviously the whole issues of CCS cost and scalability, which Sally will talk about next. And there are some ways in which CCS for coal or natural gas are not the same as CCS for biomass, but there are other ways in which they're similar. And then the issues of biomass availability, transport, environmental impact. And I think that the crucial thing is to really think about these things as cost curves. So there are some niches where biomass is going to be available at costs that are near zero and with very little environmental impact. And for those niches, in some places, various things you do with biomass, co-firing or biomass with CO2 capture and storage, are going to be much more cost and environmentally effective than almost any other thing that you can choose. The question really is how big those niches and what the supply curves look like. And so just to give you one example, this is from a paper, an ES&T paper that Jamie Rhodes and Alan Robinson and I did a long time ago. It's really focused on co-firing, but what we did is look at a state-by-state basis at biomass availability and the number of coal plants and really try and build up a supply curve for the US. And I don't want to go into detail, but the point is what you find there is there are some places where you have co-location of plants and disposal opportunities if it's biomass with capture and waste biomass supplies, and you find very cheap mitigation opportunities. But then as soon as you scale up from there, it gets harder. And that really is to do with the fact that biomass is relatively low density fuel and heterogeneous, and so transportation tends to be a problem. And the other issue is seasonal availability has to be a problem. People often sweep that under the rug, but when you think about the capital costs of plants and their availability, it turns out to be a big thing. So I think those are sort of the central challenges for biomass with CCS. The central advantage is the sense at which one can do it relatively soon in some niches with existing technologies. Indeed, by some measures, it's already happening. Then there's two more things. There's direct capture of CO2 from air, which I'll talk about a bit more later, but I think the summary is that there isn't appropriate commercial hardware developed now, and so the costs are disputed because there is no appropriate technology developed. I think you can say clearly the land footprint is very low, but energy is, well, whether it's substantial or not depends on your framing, but it's certainly for the systems we develop of order 10 gigajoules primary per ton, and in some circumstances that's a lot. And for biochar, I would say, and this is obviously another hotly disputed thing, as many of these are, I would say that there are two sorts of benefits people talk about. One is the benefit of soil amendment. And where that is true, that could be a substantial benefit, but my read of the literature is there is no data yet to suggest that that is very widely true. There is data in limited places to suggest it's true, but the question of how broadly applicable that is to different cropping conditions, different agricultural conditions is really unclear. And that's something that could be resolved by research pretty easily, but it hasn't been yet. Then there's the whole issue of just the benefit of burial, and I think the benefit of burial hangs completely on scale. If you have a very large-scale system where you have large-scale concentrated biochar, it's very hard to see why it would make any sense to bury it, since that's sort of a negative coal mine. And in a world where we still have positive coal mines, it's hard to see why you do that. But in a world where you have very distributed supplies, where the costs of movement are large and the cost of burial is small, there may be niches where that makes sense. And I think my kind of overview summary is that we don't have any kind of broad feeling of how well distributed those niches are or aren't. But I think that statement's important. That is, I think if somebody claims that there's a place where you want to do large-scale biochar in a centralized way and then make it as char, it's a little hard to see why you wouldn't rather just displace fossil fuels or do biomass with CCS. So then there are three technologies related to the oceans, and I think here there's actually, in a way, some more definitive things you can say. And so on iron for the ocean, which is where a lot of the framing of geoengineering started and much of this conversation has been anchored, my understanding from folks like Jorge Sarmiento and others who've done a lot of thinking about the ocean geochemical modeling is that there's, in a sense, a pretty clear, sharp answer. If you remove the iron limitation everywhere in the surface ocean, the most you get in terms of deep export is something of order a gigaton C. There's lots of arguments about that. Some people would say it's actually an order of magnitude lower than that. It's hard to see it's much bigger. And so this isn't a formal policy analysis. This is just a gut feeling. But my sense is that if you're talking about manipulating the whole ocean biota in a substantial way to get something that amounts to sort of 10% of emissions, that doesn't sound to me like a really exciting trade-off. That's not to say there might not be some places where niches where it makes sense, but I think that it's important to sort of think about that framing. I mean, if the question was if we manipulate the whole ocean biota this way or substantially, and I use disruption carefully because it's not necessarily all negative impacts, but if we did that and we were getting 10 or 100 gigatons a year, then you'd say, oh, that's worth really thinking hard about that trade-off. Something that gets, I think, little attention, maybe because nobody has an idea that works, is adding alkalinity to the ocean. And I think that should get attention. And the reason is the following. If you look at the costs of both environmental and capital and operating costs of mining large quantities of alkaline rocks, ultramafic rocks, or what have you, those costs in dollars a ton carbon units are pretty small. And if you ask yourself at the other end, if you say I could magically distribute dissolved magnesium in the downwelling regions of the ocean, how effective that would be, the answer, if you could magically distribute it evenly, as I understand the geochemical literature, is that would be really effective. It captures CO2 essentially for very long time scales to forever if you're talking magnesium, because the modern ocean doesn't really make magnesium carbonates very much. And it also brings the ocean pH back where you want it, so it seems like a really good thing. The problem is we have no idea how to break the link between those two. It's all about kinetics. So Jenny Stevens and I did some studies where we looked at, even if you ground these rocks to sort of tens of micron scale, where the grinding costs are getting expensive, but they're still, maybe you could live with them, you get almost no dissolution in the time it takes that particle to sink to the bottom of the ocean. So you need to do something to accelerate the kinetics, and nobody, to my knowledge, has come up with anything that is cost effective and environmentally scalable and so on. But in my view, this is something that's worth thinking about, because it's something that in principle seems to be scalable and potentially very useful. And finally, of course, macronutrients to oceans is another possibility, which I guess the one thing to say is, of course, at that point you're still forcing more carbon down into the ocean, and so this fundamental disequilibrium is there in the same way that it is with adding iron to the ocean or direct injection of CO2, but it is not if you add alkalinity. And so it's important to think about the sharp distinction between adding alkalinity on the one hand, which is much more permanent, and in some sense you can more strongly say that it gets at the root problem than things that just try and push carbon down from the surface ocean to the deep ocean. So now I want to say a little bit about the importance of niches. So you can't argue with the fact that a ton avoided is the same as a ton captured. So until we're in a world where net emissions are zero, from the point of view of the global carbon cycle, cutting emissions and CDR are indistinguishable. And since a world where we're at zero net emissions is presumably long after probably any of us in the room have anything useful to say on policy, we'll probably be dead, it's not clear that it's worth worrying that much about that world right now. And so you might say, is CDR just mitigation? And maybe the answer is yes. But I think there's some important potential advantages it gives in terms of market diversity. I want to talk a little bit about that. So a central one is that it's a back. I've got air capture on some of these slides, but this actually applies equally to all of these technologies. There's one case where it doesn't, and I'll make that clear. So, this is from a paper we had in 1992, an old paper on geoengineering that included all these CDR technologies. It was an early review paper, and it was a simple idea based on the early NAS work about why backstops are important. And obviously, this is a bit of a trick, or simplistic, but the point is in energy modeling, having something that has a supply curve that has a pretty fixed marginal supply cost, even if it's a high supply cost, is important. Because the abatement cost tends to have a high peak. There's parts, I don't know if you can see it. Can you guys, would somebody reply and tell me whether they can see the mouse? Yeah, so when you get, obviously, the high part of the supply curve, the difficulty of, squeezing emissions out of, say, airplanes, you can get very high costs. And the ability of something, and again, I've written air capture here, but don't necessarily believe air capture in those numbers, but the ability of something to have a relatively flat supply curve is pretty important. But that understates it, because it understates the heterogeneity of the energy system and of the economic system. And that's where I think the benefits of adding more technologies, even if they seem to sort of do the same things as the ones we have, is larger than you might think because of the heterogeneity. So first of all, a word about uncertainty. So it's important to think about the carbon cycle inertia. I know I'm preaching to the choir here, but obviously nothing we do to cut emissions over the next half century has much impact on temperatures over the next half century. Cutting emissions really benefits the half century after that in simple terms. And there is this systemic uncertainty about how much climate change we get for a given amount of CO2 emissions. And if you think about kind of classic optimal climate policy in a growth model under uncertainty, you find that there are very big benefits to being able to make negative emissions in the distant future. So that's a true statement, but it's in the very distant future. And that true statement also kind of has a moral hazard problem. So, I think the thing that we all fear is that, what this paper that I just had, this climatic change paper from 2006 essentially says, if you're hard-nosed about it, is if you know you have a technology that can pull CO2 out of the air, even at very high cost, $1,000 a ton carbon numbers, if you know you have one of those that could be useful in 2100, then because of the long inertia of the carbon cycle and the uncertainty of climate sensitivity, you're actually rational to do a little less mitigation now. That is the correct, answer from a standard economic policy model, but it's an answer that none of us are, I think, typically comfortable with, and this cartoon captures it perfectly. The search for a breakthrough technology continues, and as always with these Tolles cartoons, the punchline's at the bottom where the person says, no, that's the great thing about this technology. You don't have to rush if you've got a time machine. And in some way, of course, geochemically, negative emissions are a time machine for CO2. So the last one I really want to talk about is physical carbon arbitrage. So, why do we have carbon trading? The idea of carbon trading is that instead of just allocating the costs of cutting emissions by, say, the amount of emissions we have, we agree that all countries will see the same marginal price. So these three, without trading, each country cuts equally. These are supply curves. You can look at the key. With trading, in the classic version of trading, each country has the same marginal price. That's the basic idea of carbon trading, and that lowers the overall cost of control. So what happens when I add the possibility that some countries have supply curves that go negative, whether it's air capture or anything else? So the point is, this region is a region that's got very small total emissions, but maybe it has the possibility for some particular odd reason, because it's got very cheap solar because it's the desert, or it's got ultramafic rocks, or it's got this particularly good opportunity for biomass with capture. It's got the opportunity to have a significant amount of negative emissions at some cost. The point is that heterogeneity means that the overall cost can be lower. And so what the point of this is to say that an argument that treats the world as a single homogeneous lump and says if we say to ourselves, well, a particular technology, say biomass with capture or air capture, what have you, is not as cheap as some other things, and think about that as a kind of binary thing for the world, really misconceives the advantages you get in economic framing of releasing constraints, which comes from the heterogeneity. So one example, and this may or may not be relevant, but if you want to drive anything in the energy system, got it with solar thermal, you've got to pay attention to the fact that all of this is really the amount of solar you get against amortized capital, and there's some place in the world where you have like 2 times as much solar insolation, even as Spain, where we're building a lot of solar. And so that is a big example of heterogeneity. If you had some technology that was important that was driven off solar, whether it's air capture or something else. That's sort of, I guess I have one last comment I want to make on this, and this one only applies, it's important to say, to BECCS or direct air capture, which is making carbon neutral hydrocarbons in the long run. So all the previous things I said about heterogeneity apply in principle to any CDR technology, but this only applies to BECCS or DAC. And the idea is simply that in the long run, well, just a fact about our energy system that we pay more for liquid fuels than we do for other energies in general. And the reason is simple, because the best batteries are in my cell phone. It's very expensive with lots of money spent, still don't make a megajoule a kilogram even today, and gasoline is 40. And that advantage is large and I think not likely to be bridged. Yes, I know I'm not counting the efficiencies, but even so, it's a huge difference. And so in a world where carbon prices go up and oil prices go up, which they may not, it could conceivably make sense to actually make synthetic fuels. And if the technology of making this by a combination of methanation and the Exxon Mobil methanol gasoline process, the technology to do it is pretty clear. The hard part is getting the energy in the form of hydrogen and getting the CO2 from air capture or biomass capture. But what you get out of it is the ability to use primary energy, nuclear or solar or what have you, to produce fuels that have the very high energy density. I think there are some scenarios under which that could be important, essentially for the parts of the transportation system that we can't reach easily by electricity. So that's sort of some of the central reasons why I think you might want to bother with it. And even though it's still true that a ton not emitted is the same as a ton emitted and recaptured until you come to globally zero emissions. Thanks very much.
Thanks, David. That was, in fact, right on time. We can take a couple of questions. I will see if there's anybody in the audience. And we do absolutely need to use the microphones on this, otherwise David won't be able to hear you. Questions?
So this is Larry Baxter from BYU. Appreciated your presentation. Have you ever done an analysis of the direct air capture actually directly from air versus extremely efficient carbon capture from, for example, flue gas that captures all of the carbon that's added to the flue gas plus the CO2 that came into the air? So the point is that in the second case, you can amortize the capital cost of the process over a much larger CO2 capture, and efficiencies and costs can be quite a bit lower than just from air. I'd be interested on that.
You mean doing it in a cooling tower? I'm not sure I understand.
So
you mean actually trying to get the CO2 that came in the combustion air?
Right. And the point is that if you capture all of the CO2 that the combustion produced and some of the CO2 that came into the combustion air with the same equipment, that the cost of doing that, it would seem to me, would have to be a lot lower than doing something with air directly.
It's an interesting argument. I have not thought about it carefully. My sense is that that would certainly in a world where there were no contaminants, no scaling, and even capital costs, that would be true. In a world where there was no process integration, that's true. In the world, so speaking from the perspective of somebody trying to develop these technologies commercially, that wouldn't really be of interest to us because that doesn't fit the way we would actually make money by doing low carbon fuels.
Okay. At the risk of stepping in where the speaker could, I think I actually did a quick back of the envelope on that a little while ago, and I don't think combustion air. I don't think we actually imbibe enough combustion air to make that a scalable backstop technology like the one that David was talking about. But I did not look at the actual cost of capture.
It's certainly not scalable, and it's certainly not scalable. I think what we found in developing direct air capture technologies is you quickly find it's just a different optimization problem from post-combustion capture. It's always going to be more expensive than post-combustion because you've got to move so much more air, and you've got a higher thermodynamic barrier. But where at least where we've ended up in terms of the kind of system design choices you make, it ends up looking quite different from post-combustion capture.
Okay, thanks. There was another question?
Hi. You spoke quite a bit about adding alkalinity to the oceans. I was just wondering if you considered at all possibility of using biochar, which has got very high pH, but also, even more importantly, a very high buffer capacity, and actually utilising that for adding alkalinity to oceans, where you get a double effect from the pH effect and also from the sequestration at the same time.
No, I haven't thought about it as the answer. I mean, the work I've done here is some basic geochemistry and risk analysis, and then I, for a while, worked with some folks in Finnish university on a process that seemed promising but didn't work out. It was an attempt to find a way to make magnesium oxide from magnesium carbonates more cheaply than the straight-ahead way.
Okay. Right there in the back?
Yes. Question from Brian von Hersen from the Climate Foundation. You mentioned in your talk the notion of utilizing macronutrients to actually increase ocean productivity, either presumably through the introduction of macronutrients globally or alternatively perhaps through upwelling macronutrients. Could you discuss what you see as pros and cons with respect to that fundamental approach in terms of restoring ocean productivity on a global scale?
I think I'm really not the right person on ocean productivity to answer that. Just outside my knowledge. I mean, I can say that in terms of carbon cycle, I don't think it makes a lot of sense, because in the end, at the best, what you're doing is really exporting more carbon from the surface to the deep ocean, and it's not, and you're doing it in a way that's quite manipulative, and it's not clear to me that that would be interesting. I mean, if we're talking about large-scale things that could really manage gigaton-scale amounts of carbon, gigaton-a-year scale amounts of carbon with reasonably low environmental impact, it seems to me that adding alkalinity is far more promising. Because in the end, once you've added, I mean, the issue is how you get it there. But once you've got alkalinity there, it's very hard to see much in the way of bad side effects, and it really does buffer carbon. It's pretty simple geochemistry, especially with magnesium. But as to the importance for ocean surface productivity, I'm just not the right person.
And so is that magnesium approach fundamentally a precipitation or other deep or middle ocean?
No. I mean, if you for every mole, no, it's just you're adding alkalinity, and that's pulling CO2 out and restoring pH. And the key, there's not, in the modern ocean, we're not precipitating magnesium very much, is at least what, I'm not a geochemist, but that's what they tell me in the textbooks to say. So there's a little bit different from adding calcium, where of course you've got the lysocline and you're supersaturated, and you've got to think about how that changes over the 1,000-year time scale. But to a pretty good approximation, if you're adding alkalinity, you're taking CO2 out of the air pretty close to permanently. I mean, we're talking really, at that point, 100,000-year time scales. And you're bringing the pH back to what you'd like it to be. And there are some issues about the effect of magnesium on aragonite precipitation and whether that would alter reef growth. We looked at that a little bit in the paper with Jenny Stevens and I, but I think that it's pretty hard. I mean, I've gone around asking quite a lot of ocean folks saying, if we could get magnesium there, what would you see as the bad side effects? And we can't see many. But that's sort of a trick question, because nobody has yet any magic way to deliver a soluble magnesium ion evenly distributed over the ocean. So it's, but I think the reason I've been asking that is to focus on the fact that if you could do that, it seems it's very useful. And on the other hand, the cost in dollars a ton carbon equivalent of mining huge quantities of the ultramafic rocks and distributing to the ocean in at least 100 micron quantities, grinds, that's actually pretty cheap, like just tens of bucks a ton CO2 equivalent. So that's what makes it exciting, but the gap between those two things is kinetics.
Thank you.